defects, right? We are not going to discuss about the other defects than point defects, because point defects is the only defects that we can predict are reproducible or thermodynamic quantities. Okay? So we're going to talk about the point defects, and that is pretty much related to the electrical properties, magnetic properties, optical properties of the materials. Now, if we're talking about the metallic systems, then certainly we are not talking about the electrical properties, because metal is metal. It's always a conducting. So we are not going to manipulate any resistance electrical properties of the metals. Metal is just metal, it's conductor. So if you want to talk about, okay, point defects in the metal systems, what we are going to do is the equilibrium concentration of vacancies at any given temperature. These vacancies is very important in the metallic systems. Okay? And everything is in the materials that is given, uploaded in as a PDF file. You can have all those documents, right? So you don't have to write down anything. I just follow that what's in there, okay? The free energy of a random solid solution of a vacancy in a metal is going to be G is equal to H minus Ts, okay? And if in neglecting PV terms, in other words, we are not, we just ignore the volume changes or pressure changes and so forth, which is reasonable in most of the cases. We can see G is internal energy, U minus Ts, instead of H, enthalpy here. And for the internal energies, we use a term, a simple nearest neighbors. And that the simple nearest neighbor model is nothing but total energy, total bonding energy is equal to bonding for each pair of nearest neighbor atoms. Then at absolute zero temperature. And G is the coordination number. X is equal to point defects. Atomic fraction. Here the point defects may be, it can be vacancies or solute. Right? And 1 minus x is atomic fraction of A, which is a solvent, atoms. So basically what we try to do is we try to get the internal energies. How can we make an expression of the internal energy of the certain temperature so that we can deduce the equilibrium concentration, equilibrium states of those point defects. Let me give you the final conclusions that we are going to get out of this discussion here first, before we go any further. What we're going to have is that this is a concentration of the point defects, and this is the 1 over T, the Arrhenius type plot, okay? And then we want to have a straight line so that we want to deduce the governing equations which can relate the concentration of point defects with respect to the reciprocal of the temperature. Okay? So if we succeeded to have an equation which can relate these two parameters as a straight line like this, then the slope is corresponding to some activation energy, and we want to find out what is that. Okay? And then we can find this extreme end, the cross sections, intersection, this point. What is this values? These two we want to deduce from the discussions, with the discussions. Okay. Then 3 possible bonding states. Let me continue. 3 possible bonding types available in the system is going to be AA and AV, the vacancies, the point defects are the vacancies, and then VV, right? And then we have N atomic site per cube. Then AA concentration, bonding concentration is going to be 1 minus G, 1 minus X, 1/2. That is NG over 2, 1 minus X squared. Okay. Here the G is coordination number. And VV is going to be NZ over 2X squared. And AV is going to be NGX 1 minus X. And things like that. Okay? And the total energy is just a summation of this. total energy now is going to be U, that is UAA. That's the bonding energies of AA. And then the concentration of free bonding and the internal energy, and AV, UAV. Yeah, simple as that. And that is NZ over 2, 1 minus x over square UAA plus x square UVV plus 2x 1 minus x UAV. And then that is going to be 2 NZ 1 minus x AA plus x U V plus 2x 1 minus x. And here we have UAV minus 2 UAA plus UVV. You have to notice this term here, because UAV minus UAA plus UVV, this term is going to be called interaction energy. That is UI. Okay? So UI, if UI is less than 0, that means AV bonding is preferable. That is, it tends to make a compounds. Okay? But if UI is greater than 0, that means AA or VV is preferable. That means the segregation, clustering, precipitation, things like this, precipitation. This kind of thing will happen, okay? Now, for any temperature, U is going to be NZ over 2, 1 minus x UAA plus x UVV plus 2x 1 minus x UI plus XCR PV and 1 minus X CPA dt for any temperature. That has been for the absolute 0 temperature, but you can extend the idea for any temperature by adding these two terms. You can extend the equations. Now Sm is the entropy, mixing entropy term. Mixing entropy is related of course, there's a number of possible ways. For mixing, right? Then we go into statistics, factorial thing, xn factorial 1 minus xn factorial. Here the n lattice size per cube. Okay. We use the Stirling approximations. You can simplify that factorial thing. Stirling approximation. Well, 2 pi y probably we use that approximations to that equation, then we can simplify this equation into x ln x plus 1 minus x ln 1 minus x, and use the Boltzmann relation. That is a configurational entropy Sm is equal to minus kn x ln x plus 1 minus x ln 1 minus x. Okay, now for vibrational entropy, SV is equal to CPA over T dt plus NG over 2 x squared as VV plus NGX 1 minus x as free AV. Here the S free AV and S free VV is increased vibrational entropy due to presence of AV pairs. instead of AA in a pure material. And SVV is same thing of divacancy. So, free energy per Q at a certain temperature T. G is equal to U minus TSM minus TS free. And that is now Ng over 2, 1 minus X UAA, X U VV, 1 minus X Y plus CP terms plus NKT X ln X 1 minus X TS 3 times. Then now define the equilibrium state. Means minimum energy. So we take a derivative of these free energies with respect to the x, dg over dx, and then du over dx minus t dsm over dx minus t dx free dx. So first, du over dx term, du over dx is equal to d over dx Nz over 2, 1 minus x squared UAA plus x squared U free plus 2x 1 minus x UA free. Now, if x is small, second order terms neglected. Then du over dx now can be said as dx and g uaa plus xg uav minus uaa. Here this term as bonding energy of pure solid. In other words, the host atoms. here, this term, the bonding additional due to presence of defect. Well, now ZUAV minus UAA is going to be energy of formation or heat of solution or vacancies. Which is UF. du over dx now is equal to d over dx and a plus x uf and uf. Configurational or mixing entropy term d over dx tsm equal minus nkt. For vibrational entropy which is the similar equations Ts free and Zt again, the second term we neglected. Dx Now we have this equation, and then now we can make a plot of this. Here, the slope is now, if it is 1 over t, and this is ln x, slope is now going to be minus this, the internal energy, and then the intersection here is going to be GS VAV